In this lecture, we will get introduced to a very important theorem in mechanics called Work-Energy Theorem, which is essentially work done is the increase or change in kinetic energy. So what is kinetic energy? We will talk about that, and we will also talk about mechanical energy. What are the forms of kinetic energy? We will see that. What is the expression for kinetic energy? It only depends on the speed and the mass, and therefore there is a relationship between kinetic energy and linear momentum of a body. Although one is a scalar quantity, the other is a vector quantity, there is a relationship between their magnitudes. But we will start the lecture by first talking about power, which is the rate of doing work. So essentially, we are talking about work, energy, and power in this entire chapter. Welcome to the portals of real learning. Enjoy your learning. So last time we talked about what is work, namely F dot S, and we saw various situations when the work done by a force could be positive, negative, or zero. And we also talked about energy. In this session, we will talk about power and kinetic energy, and we will also develop the work-energy theorem. Power is the rate of doing work. Work is itself scalar, so power is work done by time taken, so that is also a scalar quantity. Work done is joules, time is seconds, so joules per second. That is a unit of power, and we give a name watt. 1 joule of work, if it is done in 1 second, then 1 watt of power is delivered by that power source, or it is expended on the body on which work is being done. Interestingly, power is work by time, work is force dot displacement, but displacement upon time is velocity. So power is also force into velocity, and this not just into, it is force dot velocity once again. By now, you are an expert on dot product, right? So work is F dot S and power is force dot velocity. The power of a source depends on how much work is being done and how much time is taken by it. It's a ratio. If you do more work, then you are more powerful as long as the time taken is the same. If you do the same work in less time, again you're more powerful. Like if a boy climbs a flight of stairs in 1 minute and another boy of the same mass does that in 2 minutes, then the first boy is twice more powerful. 1 kilowatt is 1000 watt, 10 to the power 3. 1 megawatt is 10 to the power 6, 1 gigawatt is 10 to the power 9, milliwatt is 10 to the power minus 3, microwatt is 10 to the power minus 6. In MKS, power is energy by time, so energy is work or force into distance. Force itself is mass times acceleration. So kilogram meter per second squared, that is force. And you multiply that by the distance. Distance is in meters. So kg meter squared per second squared, that much is energy divided by time. So we have a cubed in the denominator for this S. This S is not displacement, it is seconds. In CGS unit, erg per second, because erg is a unit of work. 1 joule was 10 to the power 7 erg. We learned that last time. So 1 watt is 10 to the power 7 ergs per second. Traditionally, we have used another unit of power called horsepower, which is exactly 746 watts. The idea is that in olden times, they were using the horse to do a lot of work, and to know how much work a typical horse would do, they made a horse run with a rope tied around his back, and the rope was going through a pulley, and the pulley was going into a well, and a bucket of water had to be lifted. So how soon he can lift the bucket of water was a measure of the rate of doing work. And that was measured to be 746 watts. The SI unit is watts. Just to tabulate work versus power and energy versus power. What is work? Work done by a force is force into displacement in the direction of the force. Power of a source is the rate of doing work by it. The work doesn't depend on time, but the power spent or delivered depends on the time over which that work was done. SI unit of work is joule, SI unit of power is watts. Energy versus power. Energy is the capacity to do work, and power is the energy spent or delivered by it in 1 second. We are relating energy and power now. Energy spent does not depend on time, but power definitely depends on time over which the work is done or over which the energy is spent. SI unit of energy is joules, and for this it is watts. Let us do some numericals just to build our confidence about all these topics. Suppose a boy of mass 40 kg runs up a flight of 50 steps, and each step is 10 centimeter high. The time taken by him is 14 seconds. What was the work done by the boy and what was the power developed? Take G as 9.8. We can calculate the work done. We have learned that already, plus mgh. What is the total height? 50 steps, and each is 10 centimeter high. So this is actually zero point 0.1 meter. We have to use SI unit, so it is 5 meters. Work done is plus mgh. mgh 1960 joules. Power, that same work divided by the time taken to do so, 1960 by 14, 140 watts. Clear? Second, a man pulls a cart at a constant speed of 16 meters per second by applying a force of 200 newtons. What is the power spent or delivered by the man? Power is force dot velocity. In this case, force and velocity are in the same direction. So force dot velocity becomes simply magnitude of force into the magnitude of velocity. Force into velocity, 3200 watts. Third, the work done by the human heart is 1 joules per beat. Calculate the power of the heart if it beats 72 times in 1 minute. Work done is 1 joule per beat. If you want to know the power, you have to see how much work is being done per second. So, number of beats per second, 72 beats in 1 minute. That is in 60 seconds. 72 beats in 60 seconds. So, number of beats per second is 72 by 60, 1.2. In each beat, it is doing 1 joule of work. In each beat. And number of beats in 1 second is 1.2. So the work done per second is 1.2 joules, but work done per second is nothing but power, 1.2 watts. Another question from ICSE. There's a body here and a force of 15 Newton is required to pull the body up of mass 2 kg through a distance of 5 meter and comes here. The angle of inclination of the plane is 30 degrees. Find so many things. Let's do one by one. What is the work done by the force? That is very easy. Displacement is parallel. So work done is simply force into displacement. Fs cos 0, that is Fs 75 joules positive. Second, what is the force due to the gravity? Well, that is just the weight, mg. M is 2 kg and g is supposed to be taken as 9.8 over here. 19.6 Newton is the force of gravity. Third, what is the work done against the force due to the gravity? Now, when you're talking of work done by gravity or work done against gravity, only the vertical displacement matters. So the vertical displacement is this one. BC. How much is that? 5 sine 30. Because sine 30 is equal to BC upon 5. And sine 30 is half, so 5 into half is 2.5 meters. So this vertical displacement is 2.5 meters. Work done against gravity is mgh, only the vertical displacement. Mg we already found 19.6 into h into 2.5 gives us 49 joules. Now stop for a moment. The work done by the force was 75 joules. Work done against gravity is only 49 joules. So the work done by the force is doing work against not only gravity but some other force as well, and that other force is friction. The difference 75 minus 49, 26 joules is the work done against friction. So friction was opposing it. Isn't it lovely? We don't even know the value of the frictional force, but we are able to find out the work done by friction. Great, isn't it? All right, two other numericals. A water pump raises 50 liters of water. By the way, 1 liter is 10 to the power minus 3 cubic meter. Given the density of water as 1000 kilogram per cubic meter, this is 1 kg mass. Liter is volume. It has got a mass of 1 kg for water. So a water pump raises 50 kgs of water through a height of 25 meters in 5 seconds. What is the power that the pump supplies? Take G as 10 here. And Newton per kg. Why is it writing Newton per kg? Force upon mass is acceleration. So Newton per kg is the same as meters per second square. Interesting. Density of water is given. Now, picture is like this. 1 liter is having a mass of 1 kg and 50 liters are being moved up by 25 meters. The work done is mgh. Mass of 50 liters is 50 kg. G is supposed to be 10 as per the question, and the height through which it goes is 25 meters. That is the work done. What is the time taken? 5 seconds. Divide by time. So many watts. Second, if the power of a motor is 40 kilowatts, at what speed can it raise a load of 20,000 newtons? Power is force dot velocity. In this case, force and velocity should be in the same direction in order to raise the load. So what is the speed then? Power upon force. Power is 40,000 watts. This is kilo means 1000. And the load is 20,000 newtons, so it is simply 2 meters per second. Now, let's look at some forms of energy. We'll first talk of mechanical energy. Energy has various forms. Mechanical, within mechanical we have kinetic and potential, electrical, magnetic, heat, chemical, nuclear, etc. The energy of the universe remains constant, although energy transformations can occur. And in fact, we are always interested in how to transform one form of energy to the other, like your ceiling fan is taking electrical energy as input and delivering mechanical energy as output. We are converting electrical energy into mechanical energy. Now, mechanical energy is the energy possessed by a body by virtue of two things, motion and its state. Now, this state is very interesting. What do you mean by state? In the case of mechanical energy, it relates to the position of the particle, position of the body. It is the height above the surface of Earth. Where it is will decide its energy. And that is one part of mechanical energy. That part is potential. So mechanical energy has two forms, kinetic and potential. Kinetic energy is by virtue of its motion. Potential energy is by virtue of its position when we talk of gravity, for instance. Now, potential energy itself has various kinds of forms: gravitational potential energy, electrostatic potential energy, elastic potential energy. But I'm giving the example of position in the context of gravity, where the body is, how high above the surface the body is will decide its potential energy. Larger the height, larger the potential energy. And mechanical energy is the sum of kinetic and potential. Now, if you think of kinetic energy, how can we describe it? It is the energy a body has by virtue of its motion, all right. But if a body was at rest and it was imparted a velocity v, obviously a force was involved in the process, right? Nothing moves of its own. A force was involved. Like a football was kicked, it picked up a velocity. Now it has got some kinetic energy because it is moving. Where did this kinetic energy come from? As we discussed earlier, the football's energy has increased. That means somebody has done work on it, and this work was done by the kick, the force by the kick, and the distance through which the kick moved is a work done by that force on the football. So we can say that kinetic energy is the amount of work the moving body can do. That's right. But it is also the amount of work that was done on the body to bring it from rest to this speed. That means when force does work on a body, its kinetic energy increases. Historically, we have used the kinetic energy of wind for moving our boats and ships. Today, we use the kinetic energy of flowing water to generate electricity in hydroelectric power plants. Okay, so kinetic energy is denoted by the symbol K and its expression is half mv square. M is a mass, V is a speed. And kinetic energy is always positive. It may be zero, it can never be negative. Why? Mass is positive and speed, it depends on the speed. It doesn't care about the direction. If a body is going this way or a body is going the opposite way, it is not that one kinetic energy is positive and the other kinetic energy is negative. It doesn't care about the direction, it only cares about the speed. Half mv square. More accurately, it is v dot v, because if we do v dot v, what does it mean? Magnitude of the first vector into the magnitude of the second vector into the cos of the angle between them. Obviously, that is zero, so that is v square. So v square is v dot v. Where does this expression come from? Let us see that. As I said, Ke is equivalent to the amount of work an external agency has to do in order to stop it, or the amount of work an external agency has to do to bring it to this speed from rest. So suppose a body of mass m is moving with the speed v. Let a constant opposing force F act on it, creating a uniform retardation A. Let the body move a distance s before stopping. So, using this concept, we can say kinetic energy of the body is the work done by the retarding force in stopping it. And the distance traveled was s and the force was F. So this was the work done by the retarding force, and that is numerically equal to the kinetic energy. But force is ma, and force is constant, so A is also constant. Therefore, we can use this equation. Final velocity is 0. So S is equal to u square by 2a. I know it is minus u square by 2a. And that minus comes in because acceleration is negative as it is a retardation. However, the Number wise, it is v squared divided by 2 into the magnitude of the acceleration. That is s. Now, take this s here. Kinetic energy is force ma into s. And s is v squared by 2a. What do you get? A cancels. We get half mv square. Half mv square. That's how it comes to this particular expression. Forms of kinetic energy. It is by virtue of its motion, and what I talked about as half mv square is only for translational kind of kinetic energy, like a car moving or apple falling down, but a body can rotate, like the needle of this clock is rotating, the earth is rotating. This is rotational kinetic energy, and the expression for rotational kinetic energy is not half mv square. It is something else. Vibrational, well, you can say it is translational, but it's to and fro. So this vibrational kinetic energy also has a different expression. However, a body can have any of these three types of motion. In fact, it can have a combination of motions, translation plus rotation, or translation plus vibration, or all the three put together. So then you have different terms of kinetic energy for each type of motion, and the total kinetic energy is the summation of all of these terms. Now, let's relate kinetic energy with momentum. I know momentum is a vector. How can you relate a vector to a scalar? But I'm not going to take the momentum vector. I am going to consider the magnitude of the momentum. Half mv square, multiply and divide by m. We get m square v square here. That means mv whole square divided by m. This is m square v square, isn't it? But mv square is p square, so I can write k is equal to p square by 2m. Wonderful. There's a relationship between kinetic energy, which is a scalar, with the magnitude of the momentum. It's a very useful relationship, but caution. It is valid only for a single body. It can't always be applied like this to a system of bodies. Why? Because momentum is a vector and k is a scalar. I'll give you a very simple example. Two identical bodies are moving with identical speeds, identical masses, identical speeds, but in opposite directions. The momentum of this guy is like this, the momentum of this guy is like this. These are vectors. And when you add these two vectors, the result is zero. That means the momentum vector of the system of these two masses is zero, but the kinetic energy of the system of masses is not zero. Half mv square here, half mv square here. They can't cancel. But if you blindly use this expression, that momentum of the system is zero, so put zero here, therefore you get kinetic energy of the system as zero. That is a grave error. So this is only valid for a single body. Now let's develop the work-energy theorem. We just learned that if a force does work on a body, typically the kinetic energy is raised. Suppose I take a constant force, then acceleration is force by mass, that is also constant. So I can use this equation. V square minus u square is equal to 2as. A is F by m and s is a displacement. So actually it is acceleration dot displacement. Let us take m this side and let's take 2 this side. So half m v square minus u square, or half m v square minus half m u square is equal to F dot s. F dot s is the work done by the force, and this is final kinetic energy minus initial kinetic energy. That is change in kinetic energy. That is the work done by the force. That is work-energy theorem. The work done by a force is equal to the change in kinetic energy. Actually, not just one force. You may have hundreds of forces. Work-energy theorem is the sum of the work done by all the forces is equal to the change in kinetic energy of the body. Let's take a variable force. Variable force, kinetic energy is half mv square. So I write k as half mv square. If I say the rate of change of kinetic energy, that is kinetic energy by time, and that rate is actually written as delta k by delta t in differential form. When delta t goes to 0 or tends to 0, then it is written as dk by dt. It is also called differential. Don't worry too much about differentiation and integration. You're going to learn all of that in great detail in 11th standard. Just understand that differentiation means rate of change. So dk by dt is d dt of half mv square, and the d dt of half mv square is, there's a differentiation formula. I'm not getting into that. I finally get m into v into dv by dt. And m into dv by dt is the rate of change of velocity. So that is acceleration. M into acceleration is the force. And this v is the rate of change of position, that can be written as dr by dt. I can cancel these two dt's here, and then I can write dk is equal to f dot dr. dk is equal to f dot dr. In a very small displacement, the force can be treated to be constant, and in that small displacement, the change in kinetic energy is f dot dr. And in a displacement from some initial Ri to some final Rf, we have to do an integration from some Ri to some Rf. Kinetic energy goes from some initial value Ki to some final value Kf. This integral gives us Kf minus Ki, and this we already know. We had written earlier, remember, dw is equal to f dot ds, and w is equal to the integral of f dot ds. So on the right hand side, we have got the w. W is equal to kf minus ki, that is nothing but the same expression. So the work energy theorem is this: the change in kinetic energy of a body is equal to the work done on it by the net force, or the sum of work done by all the forces. It is the same thing. When I say all, I really mean all. The change in kinetic energy is the work done by the first one plus the work done by the second one, and so on. That means F1 dot dr plus F2 dot dr plus F3 dot dr, and so on. So I can write F1 plus F2 plus F3 etc. dot dr. Right. This is W1, work done by the first force. This is work done by the second force, and so on. So change in kinetic energy is a summation. This symbol is for summation of the work done by all the forces acting. They may be internal or external. They may be real or pseudo. Remember pseudo centrifugal force. They may be something called conservative or non-conservative. That's also another type of classification of force. All forces. Add up the work done by all the forces. That will be equal to the change in kinetic energy. It's a very powerful theorem. Some observations. It's a very powerful tool to understand energy change and energy transformations, and we'll see examples of that. It's very powerful, very elegant, and very easy to use also. There is no need for using kinematics equations in most cases. Kinematics means using those v square equal to u square plus 2as, s equal to ut plus half at square, and so on. There is no need. It simplifies the whole problem so much. However, it does not incorporate the complete dynamical information from time to time or from point to point. It only relates the state of the body at one instant or at one position versus the state of that body at some other instant or some other position. Doesn't tell us everything that went on in between. That dynamical information is not there. because it involves an integration over a period of time, and the temporal information, temporal means relating to time, is not available explicitly. Whereas Newton's second law, F equal to ma, relates force and acceleration at any instant. So such temporal information contained in Newton's law is not explicit. The theorem is in scalar form, whereas Newton's second law for three dimensions is in vector form. So the information with respect to directions also is not available. As I told you, kinetic energy doesn't care about directions. So where was the body going earlier? Where is the body going now? That information on direction is not available. So those are some limitations. If you want all of that, then you have to resort to kinematics. There is no other choice. But otherwise, you can really avoid kinematics and solve many complex problems without getting into all that. And one example was the example that we did about the inclined plane, where we got to know the work done by friction without even knowing what is the magnitude of the frictional force. Right? It's a very powerful tool. So we'll continue from here in the next session.